Hello everyone and welcome to FPGA Verilog and Vivado tutorials. In this tutorial, we explain how to define and use hardware clocks in Verilog and Vivado. As a demonstration, we explain how to generate a pulse width modulation signal that you can see over here on the oscilloscope with precisely controlled frequency and duty cycle. The experimental setup is relatively simple. It consists of Nexys A7 xilinx FPGA. However, everything explained in this tutorial applies to any other FPGA. Then, over here we have two wires. One is the ground wire, and another one is the signal wire. These two wires are attached to the oscilloscope probes, and here are the probes. The FPGA has a hardware clock with a frequency of 100 MHz. In this video tutorial, we will teach you how to use this clock and how to define pulse width modulation signals with a desired frequency and the pulse width. For example, over here you can see a train of pulses. If I now press Auto, a new acquisition will be performed. And after some time, over here you can read the frequency, the period, and the width of the pulse. You can see that the period is 5 microseconds and the width is 2.5 microseconds. And we precisely specify this period and the pulse width. We can use any other period and any other pulse width. Pulse width modulation signals are very important for controlling motors, actuators, and other mechatronic devices. Okay, let's start with explanations and with implementation. As mentioned previously, in this tutorial we are using Nexys A7 100T FPGA. This is a very popular FPGA that is often used in electrical and computer engineering programs in the US and Europe. However, everything explained in this tutorial can easily be used in the case of other FPGAs. The first step is to find the FPGA board specifications and to investigate what types of clocks the FPGA board provides, as well as the clock pin names and the numbers. Our board, that is Nexys A7 100T, includes a single 100 MHz crystal oscillator clock connected to the pin E3. This means that the period of the clock is 10 nanoseconds. And in the sequel, I will explain how to find the board specifications and how to find the clock information. Okay, first of all, open your favorite search engine, in my case Google, and search for your board name. In my case, I'm searching for Nexys A7. And over here you will see a bunch of links. In fact, I will go to the official AMD or Xilinx webpage. That is, I will click over here. Then I will go all the way down, and in Feature Documents, I'm going to click on this fourth link. And immediately a PDF document will be opened that provides a brief overview of the board, and all the information can be found over here. So let's start. First of all, we need to find information about the clock. Consequently, search for clock. And if you go all the way down, let me now search. Here you will find the section 6, Oscillator Clocks, and it's written, the Nexys DDR board includes a single 100 MHz crystal oscillator connected to pin E3, and this is the most important information. Then, there are also some other important things that we need. These are PMODs, so let's search for PMODs over here. And let's, first of all, let me go one step back, analyze what are the PMODs. So over here, you can see the PMODs. The PMODs are actually ports. You can see this one over here, this one over here, this one over here, and this one over here. we are going to use this PMOD over here and two ports on this PMOD. We are going to use ground and a signal, and I will provide a wiring diagram later on. However, for the time being, it might be interesting also to go over this section and to read what are the PMODs and what are the pin names. Over here you can see the basic cross-section of the PMOD with all the ports. You can see the VCC or the power, and you can see the ground. The VCC provides 3.3 volt signals, and over here these are the signals that you can use to send information. As mentioned previously, as a demonstration, in this tutorial we will explain how to use the clock to generate a pulse width modulation signal with the desired period, that is frequency, and the desired pulse width. And here's the wiring diagram. Over here is the PMOD port. We are going to use this one close to power supply and to this UART connector that's connected to the computer. And over here you can see the cross section of this port. We are going to use this first pin. Its hardware location is H4, that is, this is the name that you need to specify in your Verilog constraint file. And we are going to use this ground pin. Consequently, take two wires and connect them to the ground and connect them to the signal pin. In my case, the blue wire is the signal and the black wire is the ground. The ground is actually attached to this breadboard over here as well as the signal pin. Then from here, I'm using two wires that are attached to my oscilloscope probes. So what's the idea over here? We are going to use this signal to send pulse width modulation signals that are generated by the FPGA. And the signal frequency as well as the pulse width will be defined by first defining the clock. Before we jump into the Verilog and Vivado implementation, let us briefly explain how to define the clock. To define the clock, we need to edit the so-called HDC constraint file, and we need to enter these three lines. First of all, in my module, I'm going to use the port name clock or CLK. Then, I need to specify this port. I need to specify package pin. Then I need to say that this port is actually attached to the pin E3. And if you go several minutes in the past and if you watch the tutorial, I mentioned that the clock is attached to the pin E3. Consequently, the port clock is attached to E3, that is, it's attached to our clock. Next, over here in the same file, we need to enter this line. First of all, this line will create a clock whose name is system clock. You can use any other name. Then over here, we define the period. The period should match the hardware, actually the period of the hardware, that is the clock. It is 10, and the unit here is nanoseconds. Then over here, we need to specify the waveform. The number 0 over here means that the rise edge should happen at 0 nanoseconds and the fall edge should happen at 5 nanoseconds. And in this way, we generate a clock. And then we connect the clock with CLK port or the variable CLK that's used in our module. And this is the standard line. Over here we are specifying the IO standard, LVC MOS 33, and over here again we are specifying the port name. And that's it. Let's start with implementation. First, let's create a Vivado project. Click on Start and search for Vivado. In my case, I'm using Vivado 2024.1. However, you can also use any other version of Vivado, either an earlier one or a later one. It really doesn't matter. The implementation principle will be the same. So let's wait until Vivado opens. and let's start. First of all, let's click on Create Project, then let's click on Next, then let's click on Next. Keep these options as default, don't change anything, Next. And over here we need to select the board. So click on Board, click on Refresh if this is the first time you're using Vivado, and let me search for my board. It's Nexys A7 100T. If you don't see your board over here, again you need to press refresh, and after that you need to download the board files. As you can see over here, all the files are downloaded. That's why I see this minus over here. Then click on Next and click on Finish. Okay, now we are here. The first step is to define our constraint file. Consequently, click over here, then on plus, and make sure that Add or Create Constraints is selected. Then click on Next, Create File, and call the file as Constraint. And click on OK. Then click on Finish. Then expand this folder and double-click on the file. And let's edit this file. Over here, to save the time, I will simply paste the content of the file. We explained these 3 lines previously, however, let's again repeat everything. First of all, we're using this line to attach our port or variable clock to the pin E3. And again, the hardware clock is attached to the pin E3. In this way, whenever we are using clock in our module, we are actually using the hardware clock. Then over here, we are actually creating a clock. Its name is system clock, its period is 10 nanosecond, and over here we define the waveform. Rise is at 0 and the fall is at 5. And over here we connect this clock with clock variable. Over here we set the property IO standard and we specify LVC MOS 33. This is the standard name, and over here we connect this with the clock. Then over here we have another port or variable. Its name is signal. This variable will be used to generate the pulse width modulation signal in our module. And over here we attach signal to the hardware pin H4 on our PMOD. If we now go back to our wiring diagram, signal is actually attached to this pin over here, pin H4. That is the first pin of our PMOD. Good, let's continue. Then we need to specify the IO standard, and here it is. And that's it. Let's save this file and let's continue. Over here you can see a sketch of a pulse width modulation signal. Pulse width modulation is often abbreviated as PWM. To specify, or better to say to define, the PWM signal, we need to specify the period length, that is, the duration of the period of our signal, and we need to specify duty cycle, or better to say, we need to specify the pulse length. If we analyze this timing diagram, first of all, when the pulse starts, it's going to be high, and this voltage level depends on your FPGA configuration. It can be, for example, 3.3 volt, it can be 1.7 volt, or any other value. You need to look into your board specification. Then, when the pulse length is reached, that is when the time is equal to the pulse length, it goes to low value or to 0. And then again, after the period of the pulse, it repeats itself, and it goes like this. A duty cycle is defined as a ratio between the pulse length and the period length, and the duty cycle obviously can go from 0 to 1. 0 means the signal is always low, and 1 means it's a DC signal or constant signal with a constant amplitude. In between, we will have the values of pulse width modulation. For example, 60% means that the ratio of the pulse length and period length is 0.6. And this is the main principle. Now, Since we are using the clock in our design and the clock has a period of 10 nanoseconds, we need to take this clock into account when defining our pulse width modulation signal. And for that purpose, we will first use a Python code to perform basic calculations. Over here is a Python code file that I'm using to define a pulse width modulation signal. In this particular example, I'm going to define a pulse width modulation signal with a period of 5000 nanoseconds. This is basically the frequency of 200,000 Hertz and a duty cycle of 50%. So let's start. First of all, we import numpy as np, and over here we define the FPGA clock period in nanoseconds. The period of my FPGA, that is the period of the clock of the FPGA, is 10 nanoseconds. Over here, I define the desired period of the pulse width modulation signal in nanoseconds. It is 5000. Then I'm defining the duty cycle. Then, over here, I'm defining the pulse width in nanosecond. I'm simply multiplying the duty cycle with the period of the pulse width modulation signal. However, the story doesn't end there. We need to get the values that are expressed in clock cycles. This is very important when implementing. Namely, our code will be triggered on every positive edge of the clock. And the time period between two consecutive or neighboring positive edges is 10 nanoseconds. And consequently, all the calculations need to be expressed in clock cycles. To get the period length expressed in the clock cycle and to get the pulse length expressed in the clock cycle, we simply need to divide period PWM, that is the period in nanoseconds, by the period of the clock of the FPGA, that is divided by 10. And we do the same thing with the pulse length. Pulse length expressed in clock cycles is simply the width in time of our pulse divided by the clock period of FPGA. So let's evaluate this and let's see the result over here. So the period length expressed in clock cycles will be 500 clock cycles. If we multiply this with the period of our clock, that is by 10 nanoseconds, we will actually obtain 5000 nanoseconds. Then the pulse length is 250, and that's precisely 50% of duty cycles. Now that we have calculated the period length and the pulse length expressed in clock cycles, we can continue with the Verilog implementation. The next step is to create a module that will generate a pulse width modulation signal. Consequently, expand this window, click on Design Sources, then click on Plus, then click on Add or Create Design Sources, then Next, click on Create File, and I will call my module as main_module, and click on OK, and click on Finish, and click on OK, and click on Yes. And after some time, under Design Sources, you'll see Main Module. Double click on it and let's start editing. Over here, to save time, I'm going to erase everything and I'm going to paste the content of my module. And let's explain this code line by line. First of all, we are using the time scale 1 nanosecond, and this is a unit of time. And this is precisely what we want, since in the constraint file, the period of our clock is expressed in nanoseconds. The module's name is main_module. It has two ports. It has the input port clock and the output port signal. Note that both of these names are precisely the names that are used in the constraint file. Consequently, over here we have clock and we have signal. And now, the ports of our main module are connected with these variable names, or better to say with ports, in our constraint file. And we can continue. Now, over here we have clock, and clock is run periodically with a period 10 nanosecond. And we can use this clock in our Verilog code. This code will actually generate a train of pulses and it will send them to the signal port. First of all, over here, we need to declare the period length and we need to set the value of 500, and that's precisely the value that we calculated in the Python code. To repeat, this is the period of the pulse width modulation signal that is expressed in clock cycles. If we multiply this number by the value of the clock period, we will get the value of the period of our pulse width modulation signal that is expressed in nanoseconds. Over here, we declare an integer variable that will store the pulse length. And again, the pulse length is expressed in the units of clock. And it's equal to 250. And if we divide pulse length by period length, we obtain the duty cycle of 50%. Next, we declare a counter that is used to create the pulse width modulation signal. How do we create the pulse width modulation signal? The main idea over here is to use this counter to count the values until period length is reached, and then we reset the counter. In this way, the counter will count the pulse, or better to say, it will count the clock ticks until we reach the value of period length. That is, until we reach the value of 500. And it's done like this. First of all, we use the always statement. The sensitivity list is positive edge of our hardware clock. That is, this block over here is activated whenever our clock experiences a positive edge. That is, on every rising edge of the clock, this block over here is triggered. That is, on every clock tick, we are going to execute this code. So what's happening inside? If our counter is smaller than the period length, we are simply incrementing the counter. That is, if the counter is smaller than 500, we keep on incrementing the counter. And we count until we reach the period length. And once we reach the period length, we know that the pulse is completed. Then this else statement will be executed, and what do we do over here? We're simply resetting the counter. That is, we are starting from the beginning since new pulse arrives. And again, we are counting. That is, this part is executed over here. Again, once we reach the period length, we reset the counter, and that's it. Then the pulse width modulation signal is generated by using this single statement. So what's happening over here? Over here, we are actually having an if statement. This will return either the value 0 or 1. That is, it can be true or it can be false. If this condition over here is true, we're going to assign to the signal this value over here. That is, we're going to assign 1. And over here, I'm writing 1 in a bit notation. This is actually nothing less than 1 or a high value. On the other hand, if this condition over here is not satisfied, then we are returning the second value, and the signal becomes the second value over here, and that's exactly 0 in the bit notation. So what's the condition over here? If our counter is smaller than the pulse length, let's go again and see the situation. That is, if the counter is somewhere over here, it's smaller than the pulse length, what do? We are returning 1. That is, the value of our pulse width modulation signal is high. If the counter becomes larger than the pulse length, the value of the signal should be 0. And that's precisely what's stated over here. Again, over here I'm using this simple condition, and I'm checking if the counter is larger or smaller than the pulse length. If the counter is smaller than the pulse length, the value of the pulse is 1. Otherwise, the value is 0. And that's it. I'm ending the module here, and that's it. Simple as that. Of course, there are other ways of implementing pulse width modulation signals in Verilog, and I will talk more about this in my future video tutorials. So let's save everything and let's continue. The next step is to run the synthesis. Consequently, find this part over here, this block, and click on Run Synthesis and click on OK. This will run the synthesis and it will generate a preliminary design. So be patient. This step might even take a minute or so. After some time, you will see this window saying that the synthesis is successfully completed and you will be offered to run the implementation. You need to run the implementation by either clicking OK over here or by clicking over here. Let's just click OK here and let's click OK and let's continue. Again, the implementation step might even take a minute or so. Consequently, be patient. And then after some time, this window will pop up saying that implementation successfully completed. Let's click on Cancel, and the next step is to generate bit stream. Consequently, click over here and click on OK to generate the bit stream. And again, be patient. Meanwhile, attach your FPGA to your computer. For that purpose, you need to use the UART to USB cable, and after I attach, you will see this, you will hear the sound. Here it is, it's attached, while over here the write bit stream is still running. I will also turn on my oscilloscope such that I can see the signals. And let's again be patient and let's wait for a while until the bit stream is being written. Now, after this step, we need to open the hardware manager. Okay, good. Over here, let's click on Cancel. And next, let's click on Open Hardware Manager. Then over here, click on Open Target and click on Auto Connect to establish a serial communication with your FPGA. And here it is. Okay. The next step is to upload our code. Consequently, expand this window called Hardware and click over here, do the right click and click on Program Device. So let's click over here and let's click on Program. And now if you have oscilloscope attached to your FPGA, you should see the pulse width modulation signals whose period is 5000 nanoseconds and the width is 2500 nanoseconds. And that's it. Thanks for watching and see you in the next video tutorial.